Well, welcome to this discussion about the law of sines. And typically for students, this is a topic that many of them find pretty easy, at least in general. And so I hope that you also find it fairly simple as well. So let's jump in. All right. What is the law of sines? Well, the relationship we know as the law of sines can be derived from an oblique triangle. And oblique is kind of a funny word. It is nothing to do with a six pack abs. It really just means a triangle that does not have a right angle. Okay, so it's a class of triangle. Anything that is not a right triangle is classified as an oblique triangle. Okay, so in this oblique triangle, before we do anything else, I want to remind you of a couple of things. Notice that my side lengths are labeled A, B, and C, and my vertices are labeled A, B, and C as well. Now, if you are observant, you will notice that the vertex that is opposite the side length has the same letter. Just one is capital and one is lowercase. And that is true for all three of our side and vertex pairs. And that is convention. Even if it is not labeled that way, you can make that assumption. So we'll probably use that in a little bit. Now with this oblique triangle, we are going to actually drop an altitude. An altitude is nothing more than a line that connects one vertex with the opposite side and forms a right angle with the opposite side. And an altitude also serves as the height of the triangle if the side that it's connecting to is the base. Okay, so let's focus on the right triangle that occurs on the left. Okay, and I'm talking about this triangle in orange. Okay, if I'm looking at that triangle, what can you say about the sine of angle A? Sine of angle A. I think you should be able to say that that's the opposite side over the adjacent side, or H over B. And if the sine of A is side H over side B, I can go and solve for the height of the triangle by saying that that is B times the sine of angle A. Okay, now let's put that right triangle away and look at the other right triangle that's formed, the right triangle that's on the right. Is that a right triangle squared? I don't know, the right triangle on the right. Okay, that's silly math humor, but you know. Okay, so in this case, we're going to focus on this blue right triangle. We know it's a right triangle because of this notation. Even though it's on the outside, that means that this is a right angle as well. And in this case, we're going to say, all right, what can you say about the sine of angle B? And if you're looking at that carefully, you should be able to say that the sine of angle B is H over A, or opposite over hypotenuse. Okay, and so in this case, we'll go ahead and solve for the height by saying H is equal to A times the sine of angle B. Now notice that when I did this, I ended up with two different expressions that are both equal to the height. And that's useful because now I can set those expressions equal to each other. Okay, so now if they're equal to each other, I can manipulate them a little bit, and that manipulation is going to lead us to the law of sines. First thing I want to do is isolate the side length B on the left-hand side. So I'm going to multiply both sides of the equation by 1 over the sine of angle A. Okay, and when I do that, notice that this sine of angle A and this sine of angle A will cancel each other out. So the left-hand side will just be B, and the right-hand side will be A times sine of angle B all over sine of angle A. All right, so now let's multiply both sides by 1 over the sine of angle B. All right, so when I do that, notice on the right-hand side, I'll get this sine of angle B and this sine of angle B will cancel, and I'll end up with B over the sine of angle B is equal to A over the sine of angle A. Huh, okay. Well, what about angle C and side C? Well, if I flip this triangle around and look at it in another orientation, I can get the same relationship happening there. And that leads us to what is known as the law of sines. And the law of sines just says that those pairs are proportional. The length of side A over the sine of angle A is equal to the side length of B over the sine of angle B, which is also equal to the side length of C over the sine of angle C. So that allows us to do some things that we were not able to do prior to knowing this law. And in fact, we will be able to solve triangles that are oblique triangles now. Aren't you excited? Because you couldn't do that before. We can't use the Pythagorean theorem because Pythagorean theorem only works with right triangles. Well, we're dealing with obliques now. When is the law of sines used? This is clutch. You need to know when to use this tool. And really, it's key when the information that you're given about a triangle includes at least one side length as well as the opposite angle measure to one of the given side lengths. So I need to have a side length and the opposite angle measure. I need a pair for me to use the law of sines. If I don't have a pair like that, I can't use the law of sines. Two of the cases that this happens with, when I have two angle measures, like these two, like z degrees and x degrees, and the length of the included side, that's an angle side angle case. Or I've got two angle measures, there's angle z and angle x again, and the length of a non-included side. Now, if this side is the included side, then the non-included side could either be this side or that side. And in either case, this is considered an angle-angle side triangle. Okay, and there is one other case where we might use the law of sines as well, but that's going to be tackled in the next video. And that's when you have a side-side angle situation. And we'll talk about that next. We're not going to get there quite yet. So let's give it a shot. Here's an example of a triangle. And what we are asked to do with this is determine what type of triangle is shown and then solve the triangle. Round angle measures to the nearest degree and side lengths to one decimal place. Okay, so look at what you're given here. How many side lengths are given? How many angle measures are given? And what's the relationship between the side lengths and the angle measures that are given? In this case, we're given two angle measures and a non-included side. And so we would consider this an angle-angle side case, which is a prime candidate for the law of sines. So let's go ahead and solve the triangle. Take a second and organize your work by determining what you know and what is needed. Make a little table and organize what you have. And then look at what you have and decide, well, what's the best thing to do first? And if I'm looking at what I have, I know I've got two angle measures. So first thing I'm going to do is use the triangle sum theorem to find the measure of angle A. That's an easy one, right? Because the three interior angles of any triangle should sum together to equal 180 degrees. So I can set that up. Measure of angle A plus 35 degrees plus 105 degrees is equal to 180 degrees. And so the measure of angle A will become 40 degrees. So I'll go ahead and put that in my table. Now, the next thing I want to do is set a proportion using the law of sines that facilitates finding the remaining side lengths. Okay, so what was the law of sines again? The length of side A over the sine of angle A is equal to the length of side B over the sine of angle B, which is also equal to the length of side C over the sine of angle C. Okay, that's great. Now let's sub in everything we know. I know that B is going to be 7. I know that angle A is 40 degrees, angle B is 35 degrees, and angle C is 105 degrees. Okay, so there we go, just like magic. Now I have a proportion that will allow me to find the length of side A and the length of side C. Now we're going to focus on a part of the proportion at a time. We're going to focus on this part first, because with this part I can just focus on these two ratios that are equal to each other. And I'm going to cross multiply. I'm going to say side length A times the sine of 35 degrees is equal to 7 times the sine of 40 degrees. And then I'll isolate A by dividing both sides through by the sine of 35 degrees. And then I'll get an approximation for this value from my calculator, and it ends up to be about 7.845, which means that the length of side A will be about 7.8 feet when I round to 1 decimal place. That wasn't too bad. All right, let's look at the other one then. Let's focus on these two together now. Okay, so let's cross multiply again. C times the sine of 35 degrees should equal 7 times the sine of 105 degrees. Okay, and so now if I want to isolate C, I'll again divide everything through by the sine of 35 degrees and get that approximation from my calculator. C is about 11.788, which means I will say it's 11.8 feet. When you solve a triangle, one thing that is good to remember is the smallest angle measure will always be opposite the shortest side length. The smallest angle measure is measure of angle B, and the shortest side length is also side B. That's true for large angle measures as well. Here's the largest angle measure, 105 degrees, and the longest side length. So here's another example. Here is another oblique triangle, and we are going to do the exact same thing with it. We are going to determine what kind of triangle this is. I have two angle measures and the side length between them, so this is an angle side angle triangle. Another great candidate for the law of sines. So let's organize our work, fill in our table with what we know and what we need. What do you think we're going to solve for first this time? If you said the measure of angle C, you would be right. I have two angle measures, so it's easy to find the third one by using that triangle sum theorem. Okay, so 76 degrees plus 34 degrees plus the measure of angle C is equal to 180 degrees. And so that means the measure of angle C will be 70 degrees. So now, what do you think we'll do next? How are we going to find those missing side lengths? Well, if you said use that law of sines to set up a proportion, you'd be right there too. Okay, so again, here is our law of sines. Now, what is the pair that has the angle measure and the side length given? Notice that that is our C. And so I'm going to place this right in the middle instead of putting C on the outside, just so it's easy for me to grab the appropriate proportions. So instead of doing ABC, I'm going to do side length C over the sine of angle C in the middle, and side length B over the sine of angle B on the end. Okay, and so that will look like this. Side length A over the sine of 76 degrees, side length C, 9 over the sine of angle C, which is 70 degrees, and side length B, which I don't know, over the sine of 34 degrees. So again, let's go ahead and focus on one piece at a time. So this proportion will give us, when I cross multiply, A times the sine of 70 degrees is equal to 9 times the sine of 76 degrees. Divide through by the sine of 70 degrees and get an approximation from our calculator. We should get about 9.3 here. Okay, we'll put that in our table, and we'll do the same thing for the other piece. b times the sine of 70 degrees is equal to 9 times the sine of 34 degrees. Divide that through by sine of 70 degrees and get an approximation from our calculator. Okay, so let's just do a spot check. Which is my largest angle here? That would be angle A. Now, is side A the longest side? Well, yes it is. Which is the smallest angle measure? That's measure of angle B. Does that correspond to the shortest side length? And yes, indeed it does. Just a good spot check there. And that will wrap up our first video in the law of sines. In our next video, we will talk about our third class of triangles that we could potentially use law of sines with, and that is the SSA triangle. I will see you then.